Hello, and thank you for coming to my virtual Summer Seminar Day oral presentation. My name is Shelby Madruga, and I'm an aerospace engineering major at Cosumnes River College. This summer, with the support and funding of the Aerospace Mentoring Program, I was given the opportunity to work with the Dabiri Labs research group during the 2022 WAVE Fellows Program. Today, I'm going to be sharing my work on migration organization for different animal densities of brine shrimp. The agenda for today's 15-minute presentation will first aim to give an overall background and understanding of the motivation for the project. I will briefly introduce the main project and the project goals. Following the introduction, I will discuss my project, designing and executing a method to use different image processing techniques to streamline calculating the animal density of shrimp used per experiment. I'll talk about the experimental results and end on a discussion explaining the performance of the counting program versus manual verification, including the use of the method for an experiment using different animal densities of brine shrimp. Last, I'll highlight key points and ideas for future work. The goal of the project is to better understand the active diel vertical migrations of zooplankton. Every day, zooplankton make their way to the deep ocean in the morning and rise to the ocean surface as the sun sets. This process is known as diel vertical migration. There is much to learn from these migrations for swarm organization and hydrodynamics, as well as the impact the migrations may have on the climate. A singular zooplankton is small, growing to sizes of 0.1 to 10 millimeters. However, these swimmers aggregate in large swarms and are one of the largest migrations by mass in the world. The migration scale is approximately 1,000 meters, and the aggregate scale is approximately 10 meters. The flow induced by these massive migrations play a role in impacting our climate through carbon sequestration and nutrient mixing of the ocean. By deepening our understanding of this migration, we can better fight climate change and its impacts. Therefore, we decided to study this phenomenon in a lab setting. Overall, we aim to determine how the swarm changes with different animal densities of shrimp. To do this, our lab has developed a method using a scanning laser sheet to illuminate slices of the tank and a high-resolution camera to capture ultra-high-speed digital images of the animals. By imaging the illuminated animals as the laser sheets scan across the volume of the tank, the animal centroids can be reconstructed over time to form a 3D volume that closely examines the migration organization and animal movement. My individual task was to develop a method to count the number of brine shrimp added per experiment and calculate the animal number density of shrimp in the tank. I developed a method using image processing techniques in ImageJ and wrMTrck to set parameters for finding and identifying the shrimp as objects. ImageJ is a Java image processing program, and wrMTrck is a plugin for ImageJ that allows tracking of several animals. Then, to prove the usefulness of this method, I set up an experiment to determine the changes in swarm configuration with increasing animal density. I determined the number of shrimp being added to the tank during progressive tests and then captured videos of the swarm in a small tank using the shrimp's positive phototaxis to induce vertical motion. Brine shrimp, Artemia salina, are used as a model organism in this study. We purchased a half-pound of adult-grown live brine shrimp from the Northeast Brine Shrimp Company. The shrimp were stored in a large beaker with the preferred salinity of 33 parts per thousand. Then, the brine shrimp from the beaker were placed into petri dishes using a pipette. Videos of the dishes are captured using an iPhone camera at 30 frames per second. Then, processing techniques are used to count the number of shrimp, and this method is compared to a manual count to determine ground truth. For the manual counting, I acted as an observer to conduct the counting process for the 5 Petri dishes. I created a MATLAB code to help manually count the number of brine shrimp in the Petri dishes. The code counts the number of clicks on the image where I click each individual shrimp. The processing time is recorded from the start of the code to the end using the tick and talk functions to measure elapsed time. All important information is stored into an Excel program manually before further analysis. Here is a run-through of the code with Petri dish number 3. For the proposed counting method, the program ImageJ and specifically the wrMTrck plugin were used to develop a macro code for counting the brine shrimp automatically without labor-intensive work, as shown as in the manual count slide. In wrMTrck, the user is required to input a compatible file from a computer folder, convert it to 8-bit, and adjust the threshold. Here, we used a default auto threshold selection. However, the threshold could not be perfected even after several different image processing techniques, leaving smaller particles in the perimeter of the Petri dish. Finally, the user selects the parameters to be used for the tracking. We set a timer and ran the code. The results give the number of frames and tracks. Tracks are what we record as the count of brine shrimp. Here, we received a count of 161, which compared to our manual count of 158 is not too far off. The number of shrimp and processing time are recorded to an Excel program. Here is an example of the run-through of Petri dish number 3 from frames 1 to 100, and here is the video of the tracks we receive. Comparing the number of shrimp manually counted with the shrimp counted by the wrMTrck plugin count of shrimp shows good agreement between the developed method and the ground truth. Though the standard deviation increases with increasing number of shrimp, this is to be expected as wrMTrck works best with lower densities of animals. Based on these results, we believe that wrMTrck count can be a good substitute for manual counting of shrimp. In addition, for processing time, the proposed method achieved a much lower processing time compared to the manual approach, especially at higher densities. For Petri dish number 5, it took over 900 seconds to manually count the shrimp and a little over 9 seconds to count the shrimp using wrMTrck. The performance for the proposed method provides low percentage error and a faster processing time for all samples. Therefore, the proposed counting method is ideal and promising in providing an alternative solution to the manual count process. Therefore, I decided to continue my work by designing and executing an experiment with 5 Petri dishes, all of similar shrimp count with an average of 471 shrimp, and 5 tank videos. Each Petri dish's shrimp count was recorded with wrMTrck. Then, the shrimp were added into the tank sequentially, being added to the previous tank video. To induce vertical migration, I utilized the brine shrimp's positive phototaxis attraction to light. I set a light at the bottom of the tank, turned it on, let them migrate down towards the light, and then let them settle, and then after an amount of time, I turned on the light above and recorded the migration. I captured the videos with the same iPhone camera at 30 frames per second, then time-lapsed the videos. In the videos, the vertical migrations clearly have an impact on the flow as the density is increased. Particles move more frequently and lighting changes with an increase in density. This experiment shows how the migrations aggregate in a replicated lab environment. With the increase in shrimp being added, we were able to determine an estimated animal number density for each tank video. For the fish video, we got a 0.055 animals per cubic centimeter. For the next video, we got 0.153 animals per cubic centimeter. For tank video number 3, we got 0.235 animals per cubic centimeter. For the fourth video, we got 0.322 animals per cubic centimeter. And for the last tank video number 5, we got 0.414 animals per cubic centimeter. Note that observations of diel vertical migration in the ocean have shown animal number densities as high as 0.5 animals per cubic centimeter. The density in lakes even higher, up to 1 animal per cubic centimeter. This data shows a great understanding of how the animal number densities change with added shrimp. This presentation emphasizes on the importance of researching the diel vertical migrations of zooplankton. It is important to better understand the impacts of different animal density swarms to determine the overall generated flow of these large migrations. These migrations may create carbon sequestration and nutrient mixing of the ocean, impacting our climate. However, how the flow specifically contributes is still unknown. The development of a method to automatically and efficiently count brine shrimp added per experiment is crucial in determining the number animal density and a volume to find the flow differences in lower to higher density swarms. The development of this counting method provides rapid assessment and informative statistical data for further studies without the need for extra tedious work. For future applications of this method, the image segmentation and thresholding task must be improved. The images and videos we are able to capture have several issues, including low intensities, shadows, and small particles. The animals in the Dabiri lab often work with transparent animals, making them difficult to be captured and identified. These issues make our results less accurate. Going forward, sampling techniques of data collection need to be improved on in order to obtain a high-quality image or video of the brine shrimp to reduce the segmentation and thresholding process. Again, I'd like to acknowledge the financial support from the Aerospace Mentoring Program and the Caltech Undergraduate Research Wave Fellows Program. My experience in this program exceeded my expectations. Thank you to my mentors, John Dabiri and Nina Mohebbi, for opening my eyes to new stages of opportunity and encouraging me to find strength in knowledge. I am forever grateful for your guidance and useful advice. Additional thanks to the other members of the Dabiri Lab for their assistance during my summer research. I'd also like to acknowledge the Student Faculty Programs Office for their contributions to the program. Many that I mentioned today took time away from their schedules to help me in different areas, and for that I am so very thankful. To all that helped me throughout this experience, including those not mentioned, thank you. Here are my references for the images, outside observations and information, and more used in today's presentation. Thank you all for watching, and I hope you enjoyed, and if you have any questions, comments, concerns, you can comment down below in the symposium website, and I will get back to them shortly. Overall, though, I hope you enjoyed today's presentation and hope you have a great day.